International roughness index concept is basically a mechanical filter. The pavement profile is the input to this filter, and the outcome is the IRI index, which is providing some value that encapsulates the waviness of the roughness of the tested section. So to better understand how the IRI filter operates, it is instructive to evaluate its performance in the case of a sinusoidal profile as input. Injecting a pure sine with a certain frequency and amplitude as input is a very common method to interrogate linear systems, like the quarter car model simulator. The reason is that after a steady state is reached, all system components shake or vibrate at the exact same frequency as the input frequency. The amplitude will most likely, the amplitude of the different components would most likely be different, and there could be some phase lag between a certain wave and the movement of the different masses here. But the entire system components will also move in a pure sine wave way, and they would share the exact same input frequency. Another point about this is that in the Fourier sense, any pavement profile can be decomposed into pure sine profiles. So utilizing a pure sinusoidal input to the quarter car model allows us to calculate directly from the dynamic equilibrium equations the frequency response function of the system and ultimately the gain of the system. So the gain is shown here versus frequency. I will now explain how this curve is arrived at and what is the meaning of the curve. So the frequency response function analysis is a way to understand the meaning of the IRI concept. The frequency response for the IRI is defined as ZS minus ZU divided by ZP. So ZP is the input to our system. This is the pavement behaving non-smooth. And then this is the change in distance between the two masses. And the frequency response function is based on an input that is sinusoidal. By injecting a sinusoidal input to the IRI model, we can better understand the behavior of the model. We start by assuming that the pavement is exciting the model as a sinusoid. So I write this sinusoidal input. So the elevation of the pavement at any time t is some kind of an amplitude. So it's ZP with a superscript 0 to indicate a fixed amplitude, and then we have a sine with a frequency f or angular frequency omega. So omega is 2 times pi times the frequency, or if you would like to think about this as a length, wavelength instead of frequency. So we know that if a sine pavement is traversed by the IRI quarter car model, then the two masses would also, after a steady state has been achieved, would also vibrate with the same angular frequency as the pavement. There would be, of course, different amplitude for each mass, and there would be also some phase lag. So let's write this in general terms. So this is the unsprung mass. It would vibrate with some unknown amplitude, but the frequency would be the same. There would be some kind of a time lag denoted here by phi 1. And similarly, for the sprung mass, we have some kind of an amplitude, and then same frequency of excitation, but with a different phase lag. So just as a reminder for you, frequency has units of 1/2 or hertz, and the angular frequency has units of radians per second. Now, let's plug these entities into the IRI equations that were derived previously. So we need first to introduce the derivatives. Let's write the derivative of the pavement excitation is I omega. Then we have the original expression. So by deriving this expression with respect to time once, we end up with I omega and then multiplied again by the original expression. The second derivative of the pavement excitation with respect to time is then going to be minus omega squared. And again, we have the original expression here. Similarly, we can see that the ZU double prime is going to be minus omega squared ZU of t. And same for ZS double prime. It will be minus omega squared ZS of t. Let's look at the original set of equations for the IRI. That was K2 ZU minus ZS plus capital C ZU dot minus ZS dot. And here we have ZS double dot K1 ZP minus ZU plus, now there's a minus here, U times ZS ZU double prime. So this is the original set of equations. Now we plug in the sinusoidal inputs and we have the following: minus omega squared ZS equal to K2 ZU minus ZS plus C I omega ZU minus ZS. And the second equation, minus omega squared ZS equal to K1 ZP minus K1 ZU plus U omega squared ZU. So we're looking for the frequency response function, which was defined as ZS minus ZU divided by ZP. And we can write this ratio based on the two equations above. And the outcome is as follows: K1 omega squared divided by DRE plus IDIM, where DRE is U omega to the power 4 minus K1 plus K2 1 plus U, and this is multiplied by omega squared plus K1 K2, and the imaginary is C omega, then we have K1 minus 1 plus U times omega squared. Now if we have K1 omega squared divided by DRE plus IDIM, we multiply by the conjugate imaginary number, because this is imaginary, DRE minus IDIM, and then divided by DRE minus IDIM. So we are basically multiplying the frequency response function here by unity, by 1. So this is legal to do. And then if we carry out the multiplication, we get the following: K1 omega squared DRE over DRE squared plus DIM squared plus I. We have here minus K1 omega squared DIM over DRE squared plus DIM squared. And this is looking like a standard imaginary number, A plus IB. Now let's look at the gain of the frequency response. The gain is the size of the imaginary number here. Basically that means A squared plus B squared and then square root over that. And that means taking the first term here squared plus the second term here squared and then square root over that. And if we perform this, we end up with the following: that the gain is equal to the gain of, or the size of the frequency response function is equal to K1 omega squared divided by square root of DRE squared plus DIM squared. So this is the frequency response function's size, or absolute size. Few more expressions that could be useful. Wavelength. Since the pavement itself is not really a time function, but it is a physical distortion of the surface. So because we are traveling over the pavement at a constant speed of 80 kilometers per hour, it appears as if the pavement is a sinusoidal input in time, but in reality it's fixed. And if we want to switch the viewpoint from a sine function to wavelength, then we can use the following expression. So this is wavelength, and the wavelength is measured with units of length, let's say meter, and the wavelength is related to the speed of the travel in meters per second over the frequency of the sinusoidal input we used before. The period, or this could be a wavelength in space. It could also be period in time, if we are traveling with the fixed speed, would be the wavelength, let's say in meters, divided by the speed in meters per second. And of course, the frequency that we're dealing with is the speed in meters per second over the wavelength in meters. So these are just some expressions that may help convert a chart with respect to frequency to a chart with respect to wavelength. This chart shows gain versus frequency for the IRI model. It basically displays the amplitude of the change in distance between the two quarter core masses for a sine-shaped pavement profile with an amplitude of unity. So this is shown across different frequencies from 0 to 30. Gain values that are larger than unity mean amplification or heightened sensitivity, and gain values that are smaller than unity mean attenuation or reduced sensitivity. For example, if the pavement input frequency is 2 Hertz or lower than 2 Hertz, this corresponds to wavelengths of about 11 meters or longer, then the IRI gain, as can be seen here, is less than 1. This is to say that the longer the pavement wavelength above 11 meters, the more insensitive is the IRI index to these waves. Another example, let's look at a frequency of about 10 Hertz, which corresponds to a wavelength of about 2.2 meters. In this case, the gain is a bit over 1.6, which means that the IRI model is extra sensitive to this specific wavelength. Thus, the IRI index can be understood from this gain chart as a measure of the pavement roughness that is considering only a certain range of wavelengths, or in other words, a limited bandwidth of frequencies. Now, this in itself is not an issue as long as it is understood. To give one example, if an airport runway must be assessed for roughness, then the IRI index may be of little relevance because it cannot really see long waves, what is shown here as short or small frequencies, because large aircrafts are sensitive to long waves and the IRI is incapable of measuring them, then the right quality is not well captured with an IRI index. Another example is when utilizing the IRI index to represent roughness in city streets. This could also be misleading because the travel speed is much slower than 80 kilometers per hour in cities. So, although the IRI is utilized and reported by engineers across many pavement types, it is most appropriate for highways for which it was originally conceived and developed. As a reminder, the IRI is unitless, and IRI is equal to 1 over L integration over time of the sprung mass movement speed, actually, minus the speed of the unsprung mass in absolute terms, integrated with respect to time. And here we have the time of travel over distance L. This is the time required to cover the distance L, and it is equal to the speed, the length L divided by the speed, where the speed is always for the IRI model 80 kilometers per hour. And these are and L is the length over which the IRI is evaluated. So it's rather common to calculate this integral with the units of meters or inches in the US and divide by the traveled length using kilometers or miles. So many times the IRI index, even though it is unitless, is presented as meters per kilometer or inch per mile. And this bar chart shows IRI index ranges for different transportation facilities. This is just to give some feel or intuition of the expected values. The units are here shown as either meter per kilometer or inches per mile. 0 here represents absolute perfection. And here you can see new runways and superhighways. They are expected to have an IRI value of the order of 1, 0.5 up to 2 meters per kilometer. Then other pavements, new pavements, they should have an IRI of around 2, 3 meters per kilometer. As pavements get older, you get some surface imperfections, and that affects the IRI, and the value rises to somewhere around 3, 4, 5, 6 meters per kilometer. If you look at unmaintained paved roads and also severely damaged pavements, then the IRI climbs up to 10 meters per kilometer. And then rough unpaved roads, you can find the IRI values as high as 20 meters per kilometer. To provide some closure for the topics of PCI and IRI, this slide shows pictures of two vans equipped with sensors such that they can provide automated PCI and IRI evaluation while driving. For example, here you can see a beam of lasers. These lasers are shooting down and are measuring rutting while driving. There are cameras here that can generate a map of the pavement surface from which afterward the computer algorithm can detect cracks of different types, longitudinal cracks, transverse cracks, and also the severity of the cracks. This is done by 3D image reconstruction. And so at the end, it is possible to replace the assessors, the manual assessing or manual visiting of pavements, and just go with the van and survey the entire area of the lane traveled. And the IRI equipment is also built into these vans, so it is possible to obtain PCI and IRI while driving.